Now today we will see applications of slope deflection method to analyze portal frames. So analysis of portal frames using slope deflection method. So now consider a portal frame loaded and supported as shown in figure. So if you look at this frame, the frame is symmetrically loaded. Both supports are fixed, height of the column is same, moment of inertia of column is same, and BE and CF, they are the overhangs. Now we want to analyze this frame by using slope deflection method. So as usual, because this is a non-sweep type frame, this is non-sweep type frame. So first of all, we have to identify the type of frame. So this is non-sweep type frame. Now the analysis of non-sweep type frame is to be carried out exactly similar to the continuous beams. So identify unknowns. So here support A and D are fixed. So there is no question of using modified slope deflection equation. So now we can use our regular approach. So A and D are fixed. Now the slope at C and slope at B will be the unknowns. So first identify unknowns. The unknowns are theta B and theta C. So two unknowns are there. So slope at rigid joint B, slope at rigid joint C will be the unknowns. Now we can develop two equations and solve them as usual. But if you know the concept of symmetry, now this frame is symmetrically loaded, symmetrical. So now we can make use of concept of symmetry. Now using concept of symmetry, theta B equal to minus theta C. Theta B equal to minus theta C. So therefore final unknown is only one. Say theta B is the only unknown. So only one equation is required. So let's joint equilibrium equation. So this is say first step, this is second step. Now so we have chosen theta B as unknown. Therefore at joint B, so you write down the equilibrium equation. Joint equilibrium equation will be MBA plus MBC plus MBE must be equal to 0, because there are three members connected at B, BA, BC and BE. So therefore the total moment at B, the resultant moment at B must be equal to 0. So this is the joint equilibrium equation. Next step is, let's find out fixed end moments. Let's calculate fixed end moments. Now fixed end moments, as there is no load on member AB and CD, so fixed end moments for ABCD will be 0. So for BC only we have to calculate fixed end moments. That is MFBC equal to left hand, B is a left hand, minus WL square by 12. This is equal to minus W is 20. L is 6 square divided by 12. So this value will be minus 60 kilonewton meter. 60 kilonewton meter. Now similarly MFCB, because of due to symmetry, so you will get same fixed end bending moment. So this is plus 60 kilonewton meter, because the right hand generally we get clockwise moment, so clockwise is positive. So these are the fixed end moments. But due to overhanging load, we get the final moments directly. MBE will be equal to, so here you will get clockwise, acting is anti-clockwise, so reacting moment is clockwise. So this is plus WL square by 2. So W into L is the total load and their distance is L by 2. So WL square by 2. So this is equal to plus, again load is 20, this L is 2 square divided by 2, and this comes out to be 40 kilonewton meter. Now similarly MCF, this is also a final moment, MCF. So MCF will be minus WL square by 2, and this is minus 40 kilonewton meter. 40, these are the end moments due to the load on overhanging. Now we know only one unknown is there. We have one equation. Now let's develop slope deflection equations. So let's develop slope deflection equations. Let's develop slope deflection equations. So I think you do the calculations yourself. I will write down the equations only. So MAB equal to 2EI upon L 2 theta A plus theta B, and there is no delta, there is no sway, it's non-sway frame. Let's neglect delta, plus minus MFAB. So this will be 2EI, value of I is I only, divided by L is 4, this is 0, plus theta B, and this is plus minus 0, no fixed end moment. So this becomes 0.5 EI theta B. So this is equation 1. Now similarly for all member ends, let's develop the equations. MBA equal to 2EI, so divided by L is 4, L is 4, 2 theta B plus theta A 0, and delta plus minus 0, and this is also fixed end moment is 0. So this will be only EI theta B. So equation say 2. Now MBA. Next MBC. So this is equal to 2E, value of I is 2I. So value of I, let's substitute 2I. I am directly substituting the values. Divided by L is 6, 2 theta B. Now what is theta C? Theta C will be equal to, so let's substitute for theta C, so vice versa, minus theta B. So theta C will be equal to minus theta B, then this is plus minus 0, and this is minus 60. So this will be, this is 2 theta B minus theta B, it's theta B. So this is 3, 2 by 3. So 0.66, or you can write 0.67 EI theta B minus 60, equation 3. Then MCB, 2E, value of I 2I, divided by L is 6, 2 theta C, let's substitute for theta C, minus 2 theta B plus theta B, and this is plus 60. Delta is 0. So now this is minus, so this is 3. So minus theta B, so it becomes minus 2 by 3, point say 67 or 66 EI theta B plus 60. So equation 4. Then develop for CD, MCD equal to 2 EI upon L 4, 2 theta C, means it becomes minus 2 theta B. And this is now theta D is 0, plus minus 0, and this is again 0. So this is minus EI theta B, And the last MDC So MDC is equal to 2 EI upon L is 4. This is 0 minus theta B. Then this is plus minus 0. So you will get minus 0.5 EI theta B, equation 6. So we have developed 6 equations to find out the final end moments at the end of each of the member. So now that means, well, if we calculate theta B or EI theta B, we will get all these values. Now using joint equilibrium equation, let's use joint equilibrium equation and find out theta B. Say next step, using joint equilibrium equation, that is MBA plus MBC plus MBE is equal to 0. Now MBA is this, then MBC is this, and MBE, BA directly will get the value. So you substitute here, that is EI theta B, then plus 0.67 EI theta B minus 60. So this and this MBE, so this is plus 40 equal to 0. MBE was, we have calculated it was 40. So from this you will get EI theta B equal to, the answer you can check it, 13.33. So this is EI theta B. So now knowing EI theta B, so let's calculate final moments. So final moment, next step, final moments. So substitute this EI theta B in slope deflection equations 1 to 6 and find out all these values. So MAB, you will get this as clockwise plus 6.67 kilonewton meter. Then MBA, so you will get again clockwise 13.33 kilonewton meter. Then BC, MBC, so you find out this MBC, the answer may be 53.34 and anti-clockwise. Then CB, so this is again you will get 50 plus, you will get 53.34. Then MCD equal to 13.33 but anti-clockwise. And MDC, so this will be minus 6.67. So with these values, now we can construct bending moment diagram. So we have calculated the moments, bending moments, and here only you construct, the problem will be like this. For frame shown in figure, draw BMD. So only bending moment is generally asked for frame problems. See what you do, you take a reference line as a frame. Don't show any loading and supports. So just you take this frame as a reference line. First draw BMD due to loading similar to beams. Now due to loading, so this UDL WL square by 8, maximum bending moment at center, W is 20, L square, that is 36 divided by 8, and I think this value you will get 90. This is 90. And that means this will be of parabolic nature because this is UDL and this ordinate at center is 90. So this is due to loading, and due to loading, so I have drawn positive outside or sagging nature outside the frame. Now due to end moment, what you do, due to end moment, draw BMD on tension side. Draw BMD on tension side. So first you draw BMD due to loading, considering all support simple support, or this is called free BMD. Now due to end moments, let's draw BMD on tension side. Now say first one, this anti-clockwise moment, say MAB is clockwise 6.67. This is clockwise 6.67. So clockwise means it produces tension inside. It produces tension on inward side. So draw ordinate 6.67 here inside. So when you rotate the end in a clockwise direction, tension will be on inner side, and you plot ordinate inner. So here this next MVA is plus. So this is clockwise and this is 13.33. This is clockwise means this produces tension outside. This produces tension outside. So you draw a ordinate on outward side. Say this is 13.33. 13.33. Similarly here, if you see here, so MCD and DC, CD is anti-clockwise, this is anti-clockwise, this is also anti-clockwise. This causes tension outward fiber, this causes tension inward fiber. So let's draw the ordinates. This ordinate is inside, this is inside and this is outside. So this is 6.67 and this is 13.33. So for columns, due to end moments, we have drawn the BMD. Now for beam, let's say for beam, end moments, so DC and CD. This is anti-clockwise, means this is the direction, and this is clockwise. And this is 53.34, 53.34. And both produces tension upward, outside. So the tension, this is of hogging, means tension is on the upward side. So you draw the ordinates here. See, 50 ordinate is slightly more, you take slightly more. So this is 53.34, 53.34. So that produces tension outside. Now this moment is clockwise and this is 40. This moment is anti-clockwise, this is also 40. This also produces tension upward, this also produces tension upward. So there are ordinates, so 40 means somewhere here, and say this end is, this is the length. So you can draw, because that UDL is there, it varies like this. So this point, this is 40, this is 40. So, and, sorry, end of beam, I'm taking this overhang up to this end. Okay, this is the final BMD. Now the shaded area represents final bending moment diagram. the shaded area represents final BMD. So this, either you take, say this is positive, no, so due to loading this is positive, this is negative, this portion is negative, this is negative, negative. If this inside is positive, this is negative, this is negative. So this is BMD. So we have to plot a bending moment diagram in this way. Now here in other way, if you don't understand how to take the positive and negative bending moment, what you do, according to the signs plus minus, you show the directions at the end of the respective members. Then if the arrow is outward, draw ordinate perpendicular to the member inward. If arrow is inward, draw ordinate perpendicular to the member outward. So draw the ordinates of BMD opposite to the arrow. If arrow is outward, ordinate must be inward. And if arrow is inward, draw ordinate outward. So due to end moment, very easily you will get the BMD. And due to loading, you draw as usual, positive outside, negative inside. And then the net shaded area or the shaded area represents the final bending moment diagram. So let us consider another problem. So again, let's take a simple frame. So next problem, so let's take a frame, simple frame like this. Say this is fixed. This is a vertical member. And let it be fixed. And there is a support hinge here. This is 5 meter length, this is 4 meter, and this is 3 meter. So next problem, it's a simple frame, and say the moment of inertia here it is for this member 2I, for this member 3I, and for this it is say I. And this is subjected to say anti-clockwise concentrated moment of 30 kilonewton meter at joint B. Say this is A, B, C, D. Say joint B is subjected to anti-clockwise concentrated moment of 30 kilonewton meter. And this is again a simple frame. First of all, you have to identify whether the given frame is a sway frame or non-sway. Since the end is fixed, so this end, fixed end will not allow, even this end is also a hinge, even though if there is a roller, the frame, sway of frame will not occur. So this is again a non-sway type frame. Non-sway type frame. So that means we can use our regular method. So delta will not be the unknown. So again, unknowns, the first step, locate unknowns. Locate unknowns. So unknowns here, theta B, theta C will be the unknowns. Now using modified equation, using modified slope deflection equation, so unknown will be only one. Unknown, theta B is the only unknown. So we can eliminate theta C by using modified slope deflection equation for BC. So this equation is to be written for member BC at end B. So only one unknown means one equation is required. Let's write down the equation. Equation is MBA plus MBC plus MBD equal to 0, not equal to 0, because there is an external concentrated moment at the joint. If external concentrated moment is given, this is anti-clockwise, therefore minus 30. So this is the equation which we have to develop. So anti-clockwise moment of 30 kilonewton meter is acting at the joint. So now, so one unknown, one equation means problem becomes very simple. So third step is fixed end moments. Fixed end moments equal to 0 for all ends, because there is no member load. So concentrated bend moment is given, member load is not given. So this is 0. Then directly you develop slope deflection equations. Slope deflection equations. That is MAB. Now I will substitute the values directly. MAB 2EI, value of I is 2I divided by L into bracket theta A is 0. So 0 plus theta B, there is no delta and there is no bending moment, fixed end moment. So this is the only, so 0.8 EI theta B equation 1. So it's very simple problem. MBA equal to 2E, value of I is 2I divided by L is 5, 2 theta B plus 0, no fixed end moment. So this is again 8 by 5, maybe 1.6 EI theta B equation. Then MBA, MBC. Now for MBC, use modified, because further end C is a hinge support. So therefore modified we know MFBC minus MFCB upon 2 plus 3EI upon L theta B, and no delta term, so this is 0. So this is also 0. So plus this becomes 3EI divided by L is 3, theta B means EI theta B equation 3. Equation 3. So MCB is not required. Now MBD, now use our usual, because D is fixed. 2 value of I is 3I, 2EI divided by L, 2 theta B, and this is 0. So this is 6 by 4 or 3. This we can do this way. Again this 2 gets. So this is 3 EI theta B equation 4. And the last equation, MDB is equal to 2 EI, value of I is 3I divided by 4, 0 plus theta B. 0 plus theta B. And this again, this is 3 by 2, 1.5 EI theta B equation 5. So we have got 5 equations to find out the end moments for members AB, BC and BD. Now next step, using joint equilibrium equation. Joint equilibrium equation. What is that equation? MBA plus MBC plus MBD equal to minus 30. Now we substitute for MBA. MBA is this, MBC is this, and MBD